All right, so obviously solving for k and having to use the quadratic equation is a big pain. So we're going to try a different technique here that's going to make things go a lot smoother. And this is called approximation. And this is a situation that we use when k is small. Typically when k is less than or equal to anything on the order of times 10 to the negative third. I'll show you what we're talking about. Let's take an example. Here's an equation. That's NaCl, and this is a decomposition reaction that is decomposing into nitrogen monoxide and chlorine gas. And if we were going to write the equilibrium expression, it would look like this. Obviously, that is going to be the products. There is a coefficient of 2 on nitrogen monoxide, so we're going to put an exponent. And our one reactant is NaCl, and it has a coefficient of 2 as well. So let's say that we happen to know that the K for this reaction is 1.6 times 10 to the negative fifth. And obviously, that's pretty small. And what it means is that when the reaction is at equilibrium, it really doesn't make that many products. It pretty much favors the reactants. And let's keep that in mind as we do this. So let's start this off where we have initial concentrations, and they will look like this. We'll say NaCl. Initially, we'll start off with a concentration of 0.5 molar. And let's have initial concentrations of nitrogen monoxide of 0 and Cl2 of 0. Okay, so obviously these two being 0 means the reaction has to run to the products. It has to run to the right. So if we were going to write our ice table, which is going to look like this: initial, change, equilibrium, and our three species involved are, I typically write the products near the top, and I usually have the reactants near the bottom. These are both 0, and this is 0.5 molar. So we know it has to run to the right. And that means that both of our products are going to increase, and our single reactant is going to decrease. By how much? Well, here's our balanced equation, and those both have a coefficient of 2, and that has a coefficient of 1. That means our Cl2 is going to increase by x, our nitrogen monoxide is going to increase by 2x, and our it's called nitrogen hypochlorite is going to decrease by 2x. So that means that at equilibrium, this will simply be 2x, this will simply be x, and this will be 0.5 molar minus 2x. All right, here's where the magic happens. Look how small this number is, 1.6 times 10 to the negative fifth. Because 1.6 times 10 to the negative fifth is a small number, it means that x is also small, like on the order of times 10 to the negative fifth, 0.00001. And that means that no matter how big x is, that number isn't going to change very much. So what we're going to do is we're going to approximate this value. We're going to say that 2x isn't going to make a noticeable difference, and so regardless of what x is, this value is going to remain close enough to 0.5 molar that it's not going to appreciably change. This is called approximation. And so whenever we have a value of k that is small, we can approximate. All right? So that makes this a bit simpler. So when we go to solve for x, we would normally have said that k is equal to 1.6 times 10 to the negative fifth. And then, if we were going to write this out, where we know that the products are nitrogen monoxide, and that's squared, chlorine gas is to the first power, and NOCl is also squared. If we wrote this out without approximation, we'd get this. We'd get 2x squared up top times x. And on the bottom, we'd have 0.5 molar minus 2x squared. And that's going to get a little complicated. What makes it a little bit easier is that now we can approximate. And this is simply 0.5 molar squared. And that makes solving for x a lot easier. So let's do this. We're going to express this out, and so 1.6 times 10 to the negative fifth. On the top we have 2x squared times x. So 2x squared is going to be 4x squared times x is 4x cubed. And on the bottom we have 0.5 squared. So to solve for x, we're going to take 1.6 times 10 to the negative fifth. We're going to multiply this by 0.5 squared. We'll divide all of this by 4, and that equals x cubed. So let's do that. So I'm going to say on my calculator, 1.6 times 10 to the negative fifth. We're going to multiply this by 0.5 squared. That's 4 times 10 to the negative 6, and we're going to divide that, of course, by 4, and this is now 1 times 10 to the negative 6. So, to solve for x, we're simply going to extract the cubed root. You can do that on your calculator by hitting the math button. And so what I'm going to do is I'm simply going to say math. I'm going to go down to cube root, and I'm going to hit answer. So I'm taking the cubed root of my answer button. On this calculator, that's going to look like this. Let's turn this on. On, please. Okay, so let's do what I just did. We'll say 1.6 times 10 to the negative fifth, and we're going to multiply this by 0.5 squared. We get 4 times 10 to the negative 6, and we're going to divide this by 4. Now, to extract the cubed root, we're going to go up to math. I'm going to tell the calculator to take the cubed root, and I'm going to tell it to take the cubed root of that answer, 1 times 10 to the negative 6. And here is our answer, ladies and gentlemen. So x equals 0.01. Now you can plug all this stuff into here. So at equilibrium, this is 2x, 2 times 0.01, which is 0.02. This is 1 times 0.01, which is, of course, 0.01, and that stays the same. Okay, so there you go. And it makes things quite a lot easier. All right, I'll see you on the next one.